All right, Calc AB students. This is the last part of section 4.4. Hope everyone's doing well, having a good week. So this is it for 4.4. And the last thing we need to cover is the net change theorem. And to develop the net change theorem, let's start with the second fundamental theorem of calculus again. So the second fundamental theorem is if I have an integral from a to b of f prime of x dx, I know that's equal to the antiderivative of f prime of x at b, so that's going to be f of b minus f of a. Now, for the net change theorem, we just want to kind of look at this in a little bit different way. And so what I'm going to do is I'm going to actually flip this first. So I'm going to write this as f of b minus f of a is equal to the integral from a to b of f prime of x dx. Okay, so again, I want to look at this in a little bit different way. So this f prime of x, we're going to think of this as being the rate of f. And over on the left-hand side, this f of b minus f of a is going to be the change in f from a to b. And so I can rewrite this as the change in f from a to b is going to be equal to the definite integral from a to b of the rate of f dx. Okay, so to see kind of what this means, this f prime of x is going to be the rate of some quantity. Now, this quantity can be something like the rate of rainfall. In one of the AP tests is the rate of ballots that were being counted. It could be the rate of position in physics. But this f prime of x is the rate of some quantity. So I can also call that, if like we're dealing with time, is r of t, which is the rate of a quantity. Now over here on this side, this is my change in the quantity from a to b. So if I call q my quantity, this would be the change in q from a to b. So another way I can write this is the change in q, or the change in a quantity from a to b, is equal to the integral from a to b of the rate as a function of time dt. And this is the net change theorem. And we can also deconstruct this. And remember that delta q would be q final minus q initial. And that's equal to the right-hand side, which is the definite integral of the rate from a to b dt. And then I could solve for q at time b, which is q at time a, plus the integral from a to b of the rate of q dt, definite integral from a to b. And this equation down here is the same as what we were looking at in previous videos when we're using the first fundamental theorem of calculus. Okay, so let's look at an example of this. All right, so for example, let's say at 9 a.m., and we'll call 9 a.m. t equals 0 hours. It has already snowed. Three inches. And from 9 a.m. to 11 a.m., and so 11 a.m. we'll call t equals 2 hours. The rate of snowfall is modeled as the rate of snowfall is 3t squared inches per hour. So that's how the rate that it is snowing. Okay, so the first thing you want to do in part A is I want to find the net change in snow on the ground from 9 a.m. to 11 a.m. And we'll assume that there's no melting. And so I just want to find the net change of snow on the ground from 9 a.m. to 11 a.m. Okay, so I'm going to start with the net change theorem. So the change in snow from a time equals A to time equals B is going to be equal to the integral from A to B of the rate of snowfall. So my change in snowfall, in this case, from 9 a.m., which we're calling 0 hours, to 11 a.m., which is 2 hours, is going to be equal to the integral from 0 to 2 of the rate of snowfall, which is 3t squared dt. And so if I carry out this integral, I get 3t cubed over 3, so that's the antiderivative, and the 3's cancel from 0 to 2. So I get 2 cubed minus 0 cubed. And so my net change in the amount of snow on the ground between 9 a.m. and 11 a.m. is going to be 8 inches. Now, to get the units for this, let's go back up to the integral. And notice that here the rate is going to have units of inches per hour. And the time is going to be in units of hours. So those cancel. And that gives me inches. So always double check your units of these problems. So down here, the amount of snow that has fallen between 9 a.m. and 11 a.m., the net change is 8 inches. Okay, so let's go to a part B. And so for part B, I want to put down, or I want to find out how much snow has fallen. Actually, has fallen, or another way I can phrase this is how much snow is on the ground at 11 a.m. And so we're assuming there's no melting here. So I'm still going to start off with my net change theorem. So I have the net change in snowfall from 9 a.m., which is 0, to 11 a.m., which is 2 hours, is going to be equal to the integral from 0 to 2 of the rate of snowfall dt. But I want to find out the actual amount of snow. And so what I'm going to do is I'm going to take this delta S and split it into S of B minus S of A. And so I've got S of 2 is equal to So I've got S of 2 minus S of 0 is equal to the integral from 0 to 2 of the rate of snowfall dt. And what I'm really trying to find here is the amount of snow that's on the ground at 11 a.m. is going to be my S of 2. So that's going to be the snowfall at time equals 2, which is my 11 a.m. So what I'm going to do is I'm going to solve this equation I just wrote for S of 2. So S of 2 is equal to S of 0 plus the integral from 0 to 2 of R of t dt. So let's look at what this means. So this means that the amount of snow on the ground at 11 a.m. is going to be equal to the amount of snow that was already on the ground at 9 a.m., which was given as 3 inches in the original problem statement, plus the net amount of snow that fell between 9 and 11. So if we look at this, then our amount of snow on the ground at 11 a.m. is going to be equal to, all right, the first piece is the amount of snow that was already on the ground when the problem started at 9 a.m., which was given in the problem to be 3 inches, plus the net amount of snow that fell between 9 a.m. and 11 a.m., which we just calculated to be 8 inches. And so that means that the amount of snow on the ground at 11 a.m. is equal to 11 inches. Okay, now let's do a next part that's a little more tricky. Okay, so for part C, let's say from 11 a.m. to 1 p.m. And so remember that 11 a.m. is going to be t equals 2 hours, and so what that would make 1 p.m. t equals 4 hours. So from 11 a.m. to 1 p.m., snow continues to fall. Now, at a new rate, of, we'll call this P of t, is equal to 1 over 2 square root of x. 1 over 2 square root of t inches per hour. And the snow starts melting at a rate of, the melting we'll call m, so m of t, is equal to, we'll just say t inches per hour. And I want to find out how much snow is on the ground at 1 p.m. So that's at t equals 4 hours. Okay, so what we're going to do is we're going to use the net change theorem. And so I'm going to write this as delta S, so the net change of snow from here, we're just going from 2 to 4, is going to be equal to the integral from 2 to 4 of the amount of snow that has that's fallen. And so we want to look at the rate of snow fall, so that's P of t dt. And that's going to be positive because that's adding snow to the ground. But the snow is also melting at a different rate. And so we need to subtract that because that's the amount of snow that's being taken away. And so that would be the integral from 2 to 4 of m of t dt. And this delta S is going to be equal to S, the amount of snow on the ground at 1 p.m. minus the amount of snow on the ground at 11 a.m. So if I solve for what I'm looking for, which is the amount of snow on the ground at 1 p.m., which is S of 4, that's going to be equal to S of 2 plus the integral from 2 to 4 of the rate that the snow is falling minus the integral from 2 to 4 of the rate that the snow is melting. So let's look at this carefully. So here I've got the amount of snow on the ground at 11 a.m. And I just solved for that in the last problem. That was 11 inches. Plus, between 11 a.m. and 1 p.m., the snow continues to fall, but it falls at a new rate. But then also between 11 a.m. and 1 p.m., the snow starts melting at a different rate. And so all of this summed up together gives me the amount of snow that's on the ground at 1 p.m. So let's go and put in the numbers. So the amount of snow on the ground at 1 p.m. Is going to be equal to, okay, the first piece here is the amount of snow that was already on the ground at 11 a.m., which we calculated to be 11 inches in the last problem, plus the integral from 2 to 4 of the rate of snowfall, which is 1 over 2 square root of t, dt, minus the integral from 11 a.m. to 1 p.m. of the rate that the snow is melting, which is given by the equation just t dt. Okay, so S of 4 then is going to be equal to 11 inches plus the antiderivative of 1 over 2t times the square root of, sorry, 1 over 2 square root of t, you can show is equal to the square root of t. So that's from 2 to 4. Minus t squared over 2 from 2 to 4. So s of 4 is going to be equal to 11 plus square root of 4 minus the square root of 2. Minus, I'll pull out the 1/2, and that's 4 squared minus 2 squared. So I've got s of 4 is equal to 11 plus square root of 4 is 2 minus the square root of 2. And then here we've got 16 minus 4, which is 12, divided by 2, so that's minus 6. And so this gives me in total the amount of snow on the ground at 1 p.m. is going to be equal to 7 minus the square root of 2 inches. And the square root of 2 is around 1.4. So it's about 5 inches or so. So that's how we do a problem like this. So let's review again. So I've got, let's go back up here. So the amount of snowfall at 1 p.m. is equal to the amount of snow that was already on the ground at 11 a.m. plus this is the net amount of snow that has fallen from 11 a.m. to 1 p.m. minus the amount, the net change or the net amount of snow that has melted. Okay, and so for these problems, particularly on the AP test, a lot of times they will give you discrete data in a table. And so for the amount of snowfall or the amount of melting, you'd have to use the Riemann sums, midpoint rule, or the trapezoidal rule. And there's a problem like that in the homework set. And so when you do that, it's an approximation, but you set the equations up exactly the same way. You would just use whatever approximation technique that's being asked for. Okay, so there's one more video on this, and then we're done with section 4.4. So I'll see you in that video.